Okay, perfect. You can start, David.
All right, so I'm going to take this opportunity this morning to speak a little bit about the work that we've been doing over the past few years to develop molecular dynamics methods that allow you to do chemical reactions in a way that's relatively efficient and can also be very accurate, sort of the spectroscopic accuracy if you work hard enough on developing the potential. So just briefly, the structure of this presentation will be as follows. I'll talk about a range of recent studies where we've examined non-equilibrium reaction dynamics in liquids over the last few years. And there's three different systems I'll talk about. I'll talk about reaction and relaxation dynamics in weakly coupled solvents. I'll talk about reaction and relaxation dynamics in strongly coupled solvents. And I'll discuss a little bit the differences in the dynamics that you see when chemical reactions happen in a weakly and a strongly coupled environment. And finally, I'll talk a little bit about some recent systems we looked at with solvents which can dynamically steer an enantioselective product. And then in the second part of the talk, I'm going to outline a little bit the computational architecture that my colleagues and I have designed in order to efficiently carry out these simulations. And finally, taking advantage of the fact that I can give this presentation from the comfort of my own office, I'll give a brief demo of how somebody could apply this framework to a simple reactive potential energy surface. So I have a little example that's also downloadable from the web. This stuff is implemented in Charm and Tinker, and it gives you an example of how to run one of these simulations. So we'll go through that sort of quick tutorial. All right, so the first thing I'm going to talk about is reaction dynamics in weakly interacting solvents. And I guess before I describe the systems that I'm going to talk about, it's important to emphasize that a lot of the systems that we've looked at over the last few years concern reaction dynamics which happen far from equilibrium. So not within the equilibrium limit, but what happens when you have lots of excess energy in particular degrees of freedom that either drives your reaction or which is deposited in a certain molecular mode in the immediate aftermath of a reaction. And this is really how chemical reactions happen in nature, right? Whenever there's a chemical reaction, it always means that you had to have some transient fluctuation that dumps a lot of energy into a particular mode in order for a reaction to happen. Similarly, once a reaction happens, it always means there's a certain subset of modes which have a highly non-equilibrium distribution of energy in them. And so the methods I'm going to describe moving on are really applicable in the equilibrium regime, but also in the non-equilibrium regime. And that's kind of one of the interesting things about these studies. So this is two of the systems that we looked at over the last few years. And here I have a video of this reaction happening. And so what you see here is a CN radical and a cyclohexane molecule next to it. And it's embedded in a dichloromethane solvent. And so what you see is that the CN has diffused to find a cyclohexane molecule somewhere in the solvent matrix. And once it's in close proximity, there's a transient fluctuation that enables it to extract the hydrogen. And so crucially, what we found here was that in dichloromethane, which is a relatively weakly coupled solvent, that in the immediate aftermath of that CN radical plucking off that hydrogen, the CH stretch in that nascent HCN has about V equals 1 quanta of excitation in the stretching motion. And so some of my colleagues here at Bristol do ultra-fast transient infrared absorption spectroscopy. And they were able to see some transient spectral signatures that suggested that perhaps there was some vibrational excitation in that nascent CH stretch of the HCN molecule. And so our simulations were really constructed so as to understand in more detail what their spectroscopic signatures meant and whether they were reasonable. Because the conventional wisdom for a lot of solution phase reactions under thermal conditions is that things are not formed with massive excesses of energy in particular vibrational modes. And so this result came as somewhat of a surprise. I'm just going to play the movie one more time so that you can really see how wildly that CH is vibrating in the immediate aftermath of the hydrogen abstraction process. And eventually that energy that is in the CH then dissipates into both the coproduct and also into the solvent modes. Okay, so one of the sort of interesting qualitative pictures that emerged from this work, which was actually used to help understand the experimental transient spectra, concerned an observation that came directly from the molecular dynamics simulations. And that's encapsulated by this little cartoon here. So on the left-hand panel, you see HCN, and the little red arrows indicate vibrational excitation in the CH stretching motion. Okay, and this is what happens immediately after the CN plucks off that hydrogen from the cyclohexane, right? So he's vibrating like mad. And what we found was the simulations indicated that immediately following that abstraction event, the energy relaxation timescale, so the rate at which the excess energy in the CH was lost to the environment, was extremely rapid, right? And then as a function of time, the rate at which the CH energy was lost to the environment slowed down. And the reason for that is encapsulated by this little schematic. So following reaction, the HCN is extremely close to its cyclohexyl radical coproduct. And it turns out that there's extremely efficient overlap between the vibration of the CH stretch in the HCN and the CH modes in the coproduct. And so just a sort of Fermi's golden rule calculation for the energy transfer rate would show if extremely efficient energy transfer owing to effective vibrational resonance between this CH and the CHs on this guy. However, what happens as a function of time is that this HCN then diffuses through the solvent matrix, the dichloromethane solvent matrix, and into the bulk solvent, into the dichloromethane bulk solvent. And what happens is that he has much less effective vibrational overlap between the CHs of the dichloromethane, and as a result, the energy transfer rate slows down. And the difference in energy transfer rates at short time versus at long time post-diffusion is about an order of magnitude, right? So it's about a factor of 10 slower in the bulk solvent than it is in the vicinity of the cyclohexyl coproduct. And so this was a sort of cartoon picture that emerged from these simulations, which actually helped to explain these two different timescales that were seen in the experiments, whose origins were unclear. All right, and so that was sort of a reaction in a weakly coupled solvent. Now I'm going to briefly couple a reaction in a strongly coupled solvent. All right, and so this is a reaction of fluorine radical plus deuterated acetonitrile, and it's embedded in a solvent of deuterated acetonitrile to make DF and the corresponding co-radical. And so again, I have a movie of this, and here I've highlighted all the solvent acetonitriles in gold, and I've highlighted 2 of them in the sort of standard VNB colors, and you'll see why in a moment. So I'm going to run this movie. You're going to see that the fluorine is going to pluck off deuterium from one of the molecules, and then what he does is he then wanders around and goes and makes a hydrogen bond with an acetonitrile molecule that happens to be in the vicinity. And again, this work was carried out in collaboration with my ultrafast colleagues, and they saw multiple timescales following the formation of the DF. And it wasn't clear exactly what the origin of those multiple timescales was, okay? And so the story turned out to be kind of interesting. So but before I tell you exactly the origin of those multiple timescales, I want to say this is a picture that I like a lot. This shows this is the same trajectory that I just showed on the previous slide. Although what this trajectory shows is it shows a time trace of over 1 picosecond of the nuclear motions for the solvent molecules, which are in blue, and for the DF molecule, which is in white. And so the D forms these sort of intricate star shapes, and then the F is the F nuclei is this sort of more rigid thing right here. And what you see here is kind of interesting. So you see that the time trace for the solvent molecules follows a sort of standard kind of motion you would expect for things that are undergoing sort of Brownian motion. So close to thermal equilibrium. Whereas the DF forms these sort of intricate interlacing star shapes. And the reason for that is because when the DF is formed, it's formed with almost V equals 3 quanta of excitation, okay? And so if you actually, so effectively what I've made here in a graphical format is a velocity, is a position autocorrelation function. If you took the velocity autocorrelation function, or even if you took the position autocorrelation function and Fourier transformed it, you would get something that would tell you about the vibrational frequencies of this nascent DF. And so one of the interesting things that you see from this picture is that once that DF is formed, he's sort of wildly vibrationally excited, even in a very strongly coupled solvent. Okay, so that was a big surprise. If something could be formed with that level of vibrational excitation in a solvent that was very strongly coupled. And the other thing you see is that he undergoes that DF undergoes rotational excursions looking for a hydrogen bonding partner. And indeed, that's similar to what we just saw in the previous video. Okay, so I just want to give you a sort of indication of the accuracy of the potential that we were the reactive dynamics potential we were using here. So one of the tests that we did with this potential was we just calculated the vibrational spectrum of the DF embedded in the solvent and also then in vacuo. And this is actually a measurement that experimentalists have carried out. So in the gas phase, the DF vibrational frequency is about 3,000 wave numbers. When it's embedded in a acetonitrile solvent, the solvatochromatic shift arises and shifts it by about 450 wave numbers or thereabouts. And as a result, you see that the DF vibrational spectrum in the acetonitrile solvent is about 2450 wave numbers. This is, I should say, these are simulation results. The experimental result in this case was about 2,560 wave numbers. So we were getting very good agreement between the one equilibrium property that we could measure quite accurately. Okay. So again, I've just shown you the equilibrium spectra here. What happens immediately following the reaction is much more interesting because now these vibrational peaks are not stationary, they move, okay? And they move for 2 reasons. okay? They move because, one, immediately following reaction, the DF has a lot of vibrational excitation. And so we know that, we know from sort of elementary physical chemistry that if you have a lot of vibrational excitation in a particular degree of freedom, it's generally redshifted with respect to the equilibrium spectrum. The other thing that also happens is in the immediate aftermath of reaction, there's no hydrogen bonding reactions, right? The hydrogen bonding reactions are something that take about a picosecond to form following reaction. And so you have this dynamic microsolvation environment. And so the spectrum that you observe of the DF immediately following reaction sort of reflects these two competing physical effects, okay? So relaxation and change in the microsolvation environment. This is sort of the cartoon picture that illustrates what's happening, and this is why this system was really interesting. This is kind of one of the key insights that came out of this. Let me just explain this plot real quick. So what I've shown on the left-hand panel is the change in the DF band center that you observe if you just take DF, solvate it in bulk acetonitrile, effectively pluck it with a non-equilibrium pluck, like I'm plucking a guitar string or something, and then I watch it relax back down to equilibrium, okay? And so what you see is that this is my spectral baseline, my 2,540 wave numbers, right, that I showed right here. When I pluck that DF with V equals 3 vibrational energy, you see a prompt redshift, okay, because now it's far from equilibrium. And then as a function of time, it blue shifts back down to its equilibrium value as the energy in that DF dissipates into the solvent environment, okay? So that's without any chemical reaction happening. Now, when the chemical reaction is happening, I have a similar phenomenon, except now I have to worry about the changing in the microsolvation environment. And it turns out that now my baseline, which is flat on the relaxation dynamics, when it's pure relaxation dynamics, when it's reactive dynamics, my baseline is changing because my microsolvation environment is changing, right? So immediately after that fluorine plucks off a deuterium, he doesn't have any hydrogen bonding partners. And so as he wanders around and finds hydrogen bonding partners, he undergoes a redshift, okay? And so this is a standard result. If I have a stretch and if I have a vibrational stretch, think of like hydrogen bonds or something. You can think of like a hydrogen bond with water or something like this. If I form a hydrogen bond, and I generally see a redshift in my spectrum. Okay, so that's exactly what happens here. There's a time scale for how long that hydrogen bond takes to form. Like I said before, it's about 1 or 2 picoseconds. But while my microsolvation environment is changing, my DF is also losing energy, right? So I have this blue shift back. And so the net result of these effects is these two effects kind of cancel each other out, right? You have a red shift in one direction owing to the changes in microsolvation, and you have a blue shift in the other direction owing to the fact that the DF is losing energy. And the net spectrum of DF that you see post-reaction is this line right here, okay, which is, you know, more or less a flat line. There's some variation there, but it's not very much. And so this was kind of one of the most interesting insights that came out of this work in terms of interpreting the experimental transient infrared absorption spectroscopy. And again, here's the sort of cartoon picture of this, okay? So this is an immediate aftermath of reaction. Again, my red arrow indicates my vibrational excitation in my DF, so V equals 3 in the initial immediately following reaction. And you see that from this simple schematic that when I pluck off a deuterium, I'm not in the correct orientation to make a hydrogen bond. I have to do a rotational excursion in order to form that hydrogen bond, as I've shown on the other side. And so this is basically how these two effects work, okay? And so at very, very short times, it turns out that the DF spectrum is actually somewhere intermediate between what you'd expect in bulk solvent and what you see in the gas phase. simply because the electrostatic interaction of hydrogen bonding, which dominates at equilibrium, hasn't yet had time to form. Okay, but this DF has all this energy, and so as a result, as described in this paper here, you actually see something that's closer to the gas phase than it is in solution in the first, 1 or 2 picoseconds following reaction. However, as time goes on, this guy makes some rotational excursions. He finds hydrogen bonding partners, and then he goes to the equilibrium limit. And as he's forming those hydrogen bonds, the energy transfer efficiency also increases. And so this is kind of different than the last picture we saw, where I'm telling you that the spectral signature of this guy at short times is actually more characteristic of the gas phase, whereas at long times it's more characteristic of what you'd expect in the bulk solvent. Okay, and so this is kind of an interesting change from the last system that we just looked at. And then the last system I'm going to talk before I kind of go into how these simulations work is exploring dynamically guided enantioselectivity selectivity. And this is some work that was carried out with my one of my collaborators here in Bristol, Professor Barry Carpenter, and outlined in this paper here. And so Barry found a really interesting system, which is characterized by this Valley Ridge potential energy surface topology. And he found this molecule here. Okay, and so what can happen with this molecule is with some thermal excitation, this N2 group can dissociate from the rest of the molecule, and then what happens is this 3-membered ring can open up. Okay, so N2 flies off, so that's effectively the barrier that you see here. There's a transition state for N2 dissociation just at the top here, so you can somewhere here in this potential energy schematic, and then once that N2 sort of flies off, this moiety can open up, and there's 2 ways that it can open up. It can open up in a way so that it twists to give the R enantiomer of this substituted allene, or it can open up in a way that gives the S enantiomer of this substituted allene. And so following the transition state for nitrogen dissociation, this is the so-called Valley Ridge inflection point, right, where it can take 2 different directions. And you see that there's a transition state that connects these 2, although these minima are so deep that effectively once it goes either this way or that way toward the S enantiomer, it's gone past the point of no return, because the kinetics for exchange along this pathway are extremely slow. And so what Barry did is really interesting. So he was curious if it was possible to guide the enantioselectivity of this reaction in different solvents. And so what he did was he set up a reactive potential for this system, and then he just literally ran simulations and computationally screened lots of different solvents. Okay, and so the hypothesis that we sort of started this work with was that perhaps if we had a chiral solvent, we would be able to amplify the enantioselectivity of this reaction. And so that was the hypothesis we tested. So the first thing that we looked at was we looked at an achiral solvent. So this is CHCl3. Ran 12,000 reactive trajectories and measured the enantiomeric excess, and you see that this is statistically 0, right? So achiral solvent, no enantiomeric excess. That was exactly what we expected. And we chose so I should say we restrained our solvent search to solvents that you can buy in a bottle, because we're actually working with experimental colleagues right now to look at whether this computational hypothesis stands the experimental test. So we specifically focused on solvents that you can buy from chemical companies. So so then we looked at some chiral solvents. We looked at the CHFCl-Br, R and S enantiomers, ran trajectories, and again you see effectively the enantiomeric excess is numerically is 0 within error bars. Then we chose this solvent right here, which is often referred to by organic chemists as TPIPA, and I've given you the chemical formula of what TPIPA is. So We chose again, it has a chiral center, so we chose it in both its R and its S forms. Ran lots of trajectories, 2,500 of each in each solvent. And here's where it gets kind of interesting, right? We saw that the enantiomeric excess in these two different solvents was about 15% plus or minus 2.1%. So I just have two trajectories here that show the formation of the R and the formation of the S embedded in the Tafipa solvent. And so you see the nitrogen wanders away, and then it can open up in either of the two different configurations. And so, the solvent is represented by a periodic box and full atomistic detail. And this is, sorry, not sure what happened there. And so the thing that we got excited about with this simulation is the fact that this solvent-induced enantioselectivity of 15% is over an order of magnitude larger than any solvent-induced enantioselective effects that have been seen before in either the theoretical or the experimental literature. And so, as I said, we're now working with a colleague to investigate this hypothesis and see if it stands up to experimental scrutiny. So now I'm going to talk a little bit about how we did these simulations. I've shown you movies and I've shown you sort of explicit atomistic detail with reactive potential energy surfaces. And I should say that for a lot of these systems, our first port of call for thinking about how to do these was QMMM. But there was a lot of problems with that approach. And so ultimately we didn't use QMMM. In the first reaction I showed you, CN plus cyclohexane and dichloromethane, the problem is really that an accurate representation of that potential, i.e. accurate enough to match into the experimentally observed energy transfer timescales within an order of magnitude, is extremely challenging for conventional DFT approaches. And that's because of a lot of multi-reference character in the CN radical. In the fluorine plus acetonitrile reaction, the nascent DF can interact very strongly with the solvent, okay? And it actually turns out that in some of the trajectories, we saw a transient deuterium transfer state where that very hot DF could transiently transfer its deuterium to the nascent solvent molecules. But these interactions are very short-lived, and also the nascent DF, as it's wandering around the solvent matrix post-reaction, you never have any idea which solvent molecule it's going to interact with, right? Because that's effectively some kind of stochastic random walk. And so, setting a QMMN active space is a real challenge when you don't know where to cut your boundaries, okay? And then in the enantioselective dynamics reactions, QMMM may have worked, but to actually converge the error bars on the enantiomeric excess enough to say anything meaningful literally requires thousands of trajectories. And so, QMMM, for all its virtues, was simply not efficient enough for us to make any sort of meaningful statistical comment. The last thing I want to say about QMMM for this system, where we're interested in non-equilibrium reaction dynamics, is that QMMM, because you have sort of weird couplings that happen on the boundaries between the QMM and the MM region, when you do QMMM for these highly excited non-equilibrium systems, you often see very weird energy flow behavior, okay? So, and this is simply because energy transfer is very sensitive to coupling. And so if I introduce spurious coupling, which is extremely important to energy flow dynamics, I get relics that are not a physical property of the system, but they're more a property of where I decided to cut my QMMM boundaries. So these are kind of the challenges of why we couldn't use QMMM for these cases. So what we did use is this MS-EBB approach. And this goes back to an old method that a lot of people have talked about for a long time. It goes back to work done by Arya Varshal. And then lots of contributions have been made to the method by lots of people since then. And I'm just so this is probably a method that a lot of people are familiar with. I'm just gonna explain it very briefly, how it works. So the whole idea is that I can construct a reactive Hamiltonian, a little matrix, call it H, from molecular mechanics basis states, okay? And so I have a basis state, which is the potential of my reactant, a basis state, which is the potential of my product. If I have my little Hamiltonian, I can put the potential of my reactant on one diagonal, the potential of my product on another diagonal. Okay, and so I've shown you here for a simple reaction how that looks. I would get something in a, assuming that my potential is described with harmonic functions. In this connectivity, I would get a parabola that looks like this. In this connectivity, I would get a parabola that looks like this. Okay, and that's simply because I have effectively two different connectivities here. One defines my reactant, and one defines my product. If I then diagonalize that matrix, get the smallest eigenvalue, I get a potential that smoothly connects these two different states. Okay, so if I just say my potential energy surface now is the lowest eigenvalue of this matrix, which I've expressed here as just a unitary transform, where U is my eigenvector matrix, and I get a potential that connects these. Okay, so for molecular dynamics, I need forces, as everybody probably knows. And to get forces, I use the Hellman-Feynman relationship. And the Hellman-Feynman relationship basically, in this context, basically says, well, if I want, now what I want is I want the gradients of my eigenvalues. So I just want the gradients of my eigenvalue matrix D. So D is a matrix that has the eigenvalues on the diagonal. So the Cartesian gradient, so Q is a vector, is my Cartesian coordinates. The Cartesian gradient is just equal to my eigenvectors, just like you've seen up here, multiplied by the gradient of my Hamiltonian matrix. So as long as I can differentiate this H, the elements in this H matrix, I can get gradients out. And then I can propagate molecular dynamics. Okay? And so in general, this is a general strategy that we've used for all this stuff. So with EVB, you get, so I've shown it for a two-state system. For the DF system I've just shown you, we use a 64 by 64 state matrix. And that was because we had to account for all these potential transient, D transfers from the nascent DF to all the potential solvent molecules in our periodic box. So, the net result is oftentimes we do these things with two states, but you can do it for n states. And so you end up with a matrix that effectively looks like this, where your diagonals are the potential energies of what I call your molecular diabatic states. Okay, so this is literally what's returned from a vanilla MD program. Any MD program you have already gives you these, right? When you ask for an energy evaluation for a particular geometry and topology, it gives you these diagonals. And then the off-diagonal matrix elements effectively are, they just couple together these molecular diabatic states, okay? So the way that we've done this over the last few years, and I should say that this is implemented in both Charm and Tinker, and I'll show you the Tinker implementation in a couple minutes, is we do this. So you can see that this matrix, if I'm doing something that's 64 by 64, now my simulation becomes 64 times more as expensive as my conventional one-state classical MD simulation would be. And so the way that we've sort of engineered this is to use MPI. So MPI is a parallel message passing interface, right? So it's a way to write multi-threaded applications. And the way that this works is as follows, okay? So what I do is I effectively have my MD program, and I have n different replicas, okay? Here I've written it as 2 plus n, but this could just be n. This is for a particular system. I have n different replicas, okay? And what I need is I need forces. I need energies and forces for all those different replicas, okay? So one way to do that would just be to do them sequentially, but then I have to wait 64 times as long, or n times as long, for my force evaluation to complete. So the way that we did it, given that most universities and most machines now have multi-core architectures, is we just said, okay, well, we'll take every single force evaluation and we'll just spawn it out as a separate MPI thread, okay? And so the nice thing about this is that you can end up just writing a very simple MPI wrapper around your favorite MD program, which just spawns out separate threads. And then each of those threads in lockstep calculate the energy. And then they calculate their own energies, they calculate their own forces. I should say that happens here. They calculate their own energy, their own forces. And then what they do is they then, there's a data reduction where they then, each of them sends their energy and forces to the master thread. So that's this MPI gather command. The master thread takes the energies and forces, puts them in the little matrix, and then it diagonalizes the matrix to obtain the eigenvalues and the eigenvectors. And then it does the forces through this Hellman-Feynman relationship. And then it takes those forces and those energies and it sends them back out to each of the individual MPI processes and says, okay, this is actually your energy and your forces, right? So do a time step propagation. Everyone has the same energy. Everyone has the same forces. Do a time step propagation. You're all going to go to the identical new geometry because I've just told you have the same energy and the same forces. But you all have different connectivities because I've set you up that way. So now when you calculate your new energy and your new forces, they're all going to be different. So then send them back to me and I'll do the diagonalization again. I'll tell you what the real ones are. And that's effectively how this works. And so this scales linearly. So the really nice thing is if assuming I have a multi-core architecture, like I said, which is, pretty common for most people doing computational work in universities or industry these days, I don't wait any longer for my MD simulation to finish, even if I have a big matrix, than I would if I just had one simulation running in the conventional way, okay? And so here's just an example of some of the reactive surfaces we've got. So this is from the recent work that's happened in 2015 for the F plus CD3 CN reaction. I should say this is in the gas phase. We also have solution phase results and free energy surfaces and things like that, but I haven't included those in this talk because they're out for publication right now. But yeah, this is fluorine pulling off that deuterium from acetonitrile. And so you see, here's my product diabatic state, here's my reactant diabatic state. These are the diabatic states. So in my program, I tell the program that this is my, this is my reactant diabat, this is my product diabat, these are the curves. The lowest eigenvalue as I step along and do a transition state here gives me this curve. And so you see there's my transition state, and that agrees extremely well with the couple cluster value. So that was 1D. If I then show you 2D, you get a higher level of detail. So this is now a comparison over these two different coordinates. So this is my fluorine, deuterium, acetonitrile. And you see that the comparison between my MSEVB model and my CCFDT F12 calculations, is sub kcal per mole accuracy. And crucially, I get the topology of the potential and the curvature qualitatively almost identically correct. And then similarly, these are for these transient deuterium transfer states I told you about earlier. So this is the nascent DF. When it has all this excess energy, you can actually transiently transfer this deuterium to the neighboring acetonitrile molecules. Here's the potential over these two coordinates. Again, comparison of my MSEVB model with my CCFDT model. And again, you see, very good.